This is a review for the quiz that we're going to take on measuring significant figures and scientific notation. I've put a little quiz game in here for you, and it's a sig fig generator. So as you go through and answer the questions, it'll tell you if you're correct or not, and keep giving you more and more to practice with. So that's something you might want to look at. So let's talk about the rules of how you find out if something is significant or not. So one rule that we know, and this is the easiest one, is that all non-zero digits are significant. So if we have something like 975, that has 3 significant figures. It's the zeros that kind of make you guys a little bit nutty. So there's 3 rules about the zeros. If you have a zero that is between 2 significant figures, then it's going to be significant. So remember, we said all non-zero digits were significant. So this is between 2 significant figures, so it counts. Zeros that fall at the end, terminal zeros after a decimal, they're significant. This would be like a measurement if we had a beam or a balance beam or something that was measuring to the 10th gram. This would be our estimated value. So it's significant. It counts. Zeros that act as spacers for the decimal, those are not significant. So for instance, if we look at 900, we know it's 900 and not 90 and not 9 because the zeros tell us how far away that decimal point is. So those do not count as significant. So what 90, 900, and 9 all have in common is they all have 1 significant digit. So these are all 1. Now if you've got a decimal point after what you think is a spaceholder 0, then that's significant. That tells you that this is an estimated digit and that will count. If the decimal point is missing, it's not a significant 0. So looking at this first value, where we have these zeros and these zeros and that 0, these are all significant. It looks like this is spacing the decimal, which it kind of is, but the rule says that if you fall between 2 significant digits, then you're significant. So those zeros that are close to the decimal point fall between the 1 and the 7, so they count. This final 0 at the end of the decimal value is considered significant, and that would be your estimated value. So all of those guys count. Versus the next one, where these 3 are acting as a spacer for the decimal, so they don't count. But the 2 of them after, those are terminal zeros, final zeros after the decimal point, and they do count. Cool thing about scientific notation, if you've noticed already as we've been working with it, is that it takes care of all those non-significant zeros. And so when you see a value in scientific notation and you're asked how many significant figures there are, that value is how many sig figs you have. All of the non-significant zeros have been placed up here in the exponent. Let's look at the rounding now. If you know which values are significant, then it's easy to round them. So generally the most significant value is going to start on the left and you're going to work your way to the right. So for the first value here, where we're saying round that value that has right now 6 significant figures, we want to round it to 4. We start with the most significant figure, which is the one on the far left, and you start to count in. So we count into 1, 2, 3, 4. So we're going to round to that 0, which is significant, remember, because it's between 2 significant digits. So in order to round, we're going to follow that rule of 5. If your value to the right is 5 or greater, that value rounds up. If it's less than 5, then these 2 disappear. So now when we're rounding, we're going to leave off that 1, 2, and we end up with 19.00. Let's look at this one here where we're rounding something that's much smaller than 1. So again, we're going to start with the most significant and count our way to the right. So again, these zeros are spacer zeros. They're not significant. Our first significant digit starts at that 9. So we're going to want to round that to 3 significant figures. So we count over 1, 2, 3, and so we're going to round that 0. So again, that 0 looks to the right and sees there's a 2, so these disappear, and now we have our 3 significant digits. Looking over for 2 significant digits, if we want to round this one down, we've got, starting from the left, we've got our 1 and our 2, and we look to the right and we see that it's a 0, so there's nothing that we can round to, so we're going to call it 19. Some people were asking, could you call it 19 point? Same thing, but it still has 2 significant figures. Now let's do some operations with those significant figures, and we're going to try some addition and some subtraction. And the rule we have to remember, it's here in red, that when you add or subtract, you round to the least number of decimal places. So when we look at our value, like 12.013 plus 10, 12.013 has 3 decimal places, and the 10 has no decimal places. So when we add those two together, we have to round to a value that has no decimal places. And when you add them together, you come up with 22. Subtracting, the same thing. We've got 20.05, which has 2 decimal places, 18.0000, which has 4 decimal places. We can only answer to 2 decimal values. So when you subtract the 18 from the 20.5, we end up with 2.05 as our significant figures. Multiplying and dividing on this column, we're going to count the value that has the least number of significant figures. So remember, when we multiply units, we're going to square them or cube them. When you divide units, if it's the same unit, they're going to cancel out. So pay attention to your units. So for this first one, 11 times 3, 11.0 times 3, you would say, okay, what's 33? And we have centimeters times centimeters, which gives us cubic centimeters. So now we go back and we check the sig figs, and we see that that 3 centimeter value only has 1 sig fig. But here in our answer, we've got 2. So this is the tricky part. Oftentimes students will say, okay, well, I can round this down to 1 sig fig. I'm just going to call it 3. But it's not 3. So let's see the place value that this actually occupies. So remember, if we're looking at 33, this 3 is in the tenth places, this 3 is in the 1 places. So we want to round it down, but we don't want it to lose its value. So think money. If you had $33 and you gave it to me to round and I gave you back 3, I think you'd be a little disgruntled. So if we keep the value of this 3, but replace the other significant 3 with something that's non-significant, then it will be rounded correctly. So the only thing that you can use in that ones place that won't count is a non-significant 0. So that's what we're going to put there. And then the units are centimeters squared. So rounding correctly goes to 30 centimeters squared, not 3. When putting large values or very, very small values into scientific notation, we're going to see that all our spaceholder zeros are going to get brushed away. So it's going to really make it easy for you to figure out how many sig figs you have when you look at a value that's written in scientific notation. So let's look at this first value that's got 6 placeholder zeros with it. So not written but implied, that decimal point is going to be the end at that last 0. So when we write something in scientific notation, we have to follow a specific format. So for something to be correct in scientific notation, we've got kind of like this template where this value here has to be a number that's less than 10, and it has to be 1 or greater. So we have values between 1 and 10, but it has to be less than 10. The value up here, your exponent, can be a positive or it can be a negative. And the sign is going to tell you if your value written in scientific notation is a very large value or it's a very small value, just by looking at the sign. So something with a negative exponent would be a value less than 1. Something with a positive exponent is going to be something that's greater than 1. So we have to fit this format right here. So going back and looking at this value, we're going to drag the decimal point between the 6 and the 5. That way we've got that value that's less than 10 but 1 or greater, and then we're going to count how many times we actually move that decimal point. So we moved it from this 0 on this side, so we moved it 3, 6 plus 2 is 8. So we moved it 8 times. This is a value that's greater than 1, so it's going to be a positive 8. So we rewrite it as 6.53 times 10 to the 8th. And don't forget the units, that's in kilometers. When we look at a value that's less than 1, like this value here, these are those spacer zeros, which we can get rid of when we put that into scientific notation. We're going to drag this decimal point so that it fits that template. Remember, less than 10, 1 or greater. And then we'll write that value down and count how many times we move that decimal place. So we have 2.35 times 10, and let's see how many times we actually had to move that. So we moved it 3, 4, 5 times, so it's times 10 to the negative 5th, since this is a value that's less than 1. Going from scientific notation to expanded notation, we're just going to put those spaceholder zeros back. So we're going to something that's got all significant figures to something that's going to have a lot of non-significant spacer zeros. So you're going to look at the sign of the exponent. So here we see in the first value it's a negative 6. So that negative tells us that it's a value less than 1. So we're going to move the decimal point to the left 6 spaces. So once we do that, we end up with 0.00001345. If you're not sure if you've done it right, move the decimal point back and see if you ended up where you started from. So if we drag the decimal back between that 1 and the 3, we count how many times? 1, 2, 3, 4, 5, 6, and we end up with that 1.345 again. That's a good way to check. Positive exponent tells you that it's a value that's much bigger than 1 or bigger than 1. So for example, the next one, 9.98 times 10 to the second. So since it's positive, it means we want to increase this value, and we're going to move that decimal point the same number that the exponent is. So we're going to move the decimal point 2 spaces to the right. And when we do that, we come up with 998. Don't forget your units there, millimeters. So before we start multiplying and dividing with values that are in scientific notation, let's remember the rules about the exponents. So when multiplying in scientific notation, you're going to add the exponents. And when dividing in scientific notation, you're going to subtract the exponents. So we are looking at 1.5 times 10 to the 3rd centimeters times 2.0 times 10 to the negative 5th centimeters. So let's take care of the exponents first. So we have 3 plus negative 5, and that's going to give us negative 2. So once we have our exponent set, we can put that down, and we're going to say times 10 to the negative 2nd. Now let's check out our units. Centimeters times centimeters gives us centimeters squared. And now we can multiply the factors. So 2 times 1.5 gives you 3. All right, so let's count our sig figs. We have 2 sig figs here, 2 sig figs here. So I'm going to call it 3.0. So our answer there is going to be 3.0 times 10 to the negative 2nd centimeters squared. Let's look at dividing. We've got 12, and if it's hard for you to see this way, you can write it this way. You can put the 12.0 times 10 to the 3rd meters over the 6 times 10 to the negative 2nd meters. So when dividing, and we have these units, meters over meters, those cancel out. So when you're dividing with the units that are the same, you're going to end up with something that has no units because they canceled. So remember we said we're going to subtract the exponents. So here we have 3 minus negative 2. And so remember, when you subtract a negative, it's the same thing as adding its opposite. So what we have here is 3 plus 2. So we see that our exponent is going to be times 10 to the 5th. Now let's divide out the factors. So 12 divided by 6 is going to be 2. Check your sig figs. 1 sig fig with 6, 3 sig figs with 12.0, so we have to report to the single sig fig. So our answer comes out to be 2 times 10 to the 5th. No units because they canceled out. When reading equipment that's used to measure, the first thing that you should do is find the smallest increment that piece of equipment will measure to. So for instance, if we're looking at this graduated cylinder, we see that it measures to the 1 mil, but in between each 1 mil increment, we have these 10 lines, which means it goes to the 10th mil. So that means when we write our measured value, we're going to have to estimate to the next decimal point. So our estimation is going to go to the 100th of a mil. So we're going to look at where that meniscus is. Remember, we always read to the bottom of the meniscus, and we see that the value is greater than 6. So it's going to be 6 point, and let's see how far it went. 1, 2, 3, 4, 5, 6. It's reading at the bottom of the meniscus, so I'm going to call it 6.6. Now I get to do my estimated value, and that's going to be a 0, because to me it looks like it's exactly on that 0.6. Looking at the triple beam balance, again, we're going to see what is the smallest incremental value that it will record to. And we've got hundreds, we've got tens, here's our ones. And in between each one, again, we see that we have these 10 hatch marks, and each one of those represents a tenth. So since it measures to the 10th, we have to estimate to the 100th. So let's go ahead and read our values. And so it's 500 is the first one. Here's our 40. Here's our 5. Now let's see what we've got. We got 5.1, 5.2, and it looks to me like it's exactly on that too. So I'm going to call it 5.20. Now it's not always going to be a 0.0 as your estimated value. If this had happened to fall in between that 2 at 0.2 and that 0.3, then I would have called it 5.45.25. So don't just think you can add a 0 and that's going to take care of your estimated value. Sometimes that works, sometimes it doesn't.